We have a function that is ideally in integral test, you need to check whether the function should be continuous, positive, and decreasing. And I think the obvious way to see is, I think you can see from whether it's increasing or decreasing. If you see the function is already decreasing, which means going down every x or every n, it means that the function is decreasing. Okay? And if we take that function as our pattern, as a sequence, and we want to make it as a series, then it will be a convergent series if the integral or the improper integral is convergent. So whenever you see a series and you think that the series can be from a function that is decreasing, you can check the integral, the improper integral. If the integration converge, it means the series will be converged. Okay, if it is diverged, and the series also diverge. But I think one weakness from the task is if it is converged, we don't really know the value, right? So it only know, oh, it's converged or it's diverged. But we can know the value at least if we try some approximation. If we can try some approximation, which we are going to see after some examples. And if you see here, I'm just showing you example from the textbook. If you have the textbook, you can see a very simple task. So we have this series, and you can check whenever you take the n, because the fraction is getting bigger when we add the n. Like we can check n equal 1, 2, 3, and it will be getting bigger, which means that in terms of the value, the function value, it will be going to decrease. So we say that, okay, this decrease, and also we know that this will be a continuous function. Okay? And if we see this series, we can also imagine as a function of x. If you remember, if we have this function, and if we take the integration from this, we are going to get the tangent inverse, right? Okay, so the obvious way for integration test to be works is if you see any function that can be easily integrated, you know it decreasing and it can be easily be integrated, you can choose the integral test. Okay. Okay, so we could see that we can take the improper integral from 1 to infinity. We can take this, and let's say this is going to be x, okay, just to help us imagine how it looks like. And then remember, in improper, we take the limit, right? And we introduce another parameter to help, so that we can distinguish every variable. So we can say, usually we use t, if you remember the improper integral. And this will be changing the infinity, and this will be t and 1. This is just to help us compute the integrations. And we can say that this integration becomes tangent inverse x from 1 to t, and we know that this will be equal to pi over 2 minus pi over 4, right? Because tangent inverse infinity is pi over 2, and for tangent inverse 1 is pi over 4, which we can conclude that this will be a converged improper integral. Then because the improper integral converges, then this series also convergent. Okay. So this is how we can use the integration test. So first is you need to check this is going to be decreasing as a function. continuous and positive function. It means it's always on the positive side of the axis. Okay? The y value is always positive. Okay, so that's the example one. Now example two, this is also I think useful example for example two. This is what we call the P series. If you remember the improper integral, we did the P test when we compare 1 over x and 1 over x squared. So this is also can be done for the series 1 over n with power of p, and we can define what kind of p, interval p, that makes the series converge or diverge. Okay? And we can also relate this p series with the geometric series we've done before. We can also see, because we can also rewrite this in terms of geometry as long as we know the ratio, right? So we can say that if p is negative, then we can write the limit for the 1 over n with power of p. If this is negative, this should be going to be it's going back to not a fractions, right? So we can say that this will be a infinity. And if p is 0, this will be equal to 1. For sure, right? And by this too, so either case, whenever p is or let me write, whenever limit is not equal 0, we know that this will be diverges by divergence test, right? And now the questions arise if p is greater than 0. So if we could see that if p is positive, then if we take the f of x 1 over x to the power of p, this is going to be continuous function, positive, and it's decreasing function. Just we mentioned from the previous example. So this is continuous, positive, and decreasing. On we could say from 1 to infinity. Okay. And so from the improper integral, if you take the p-test series, but I will skip that. I hope you still remember the p-test. I will just write that if we have this form, this will be converges if p is greater 1 and diverge if p is less equal 1. This is from the improper integral. And using the same argument or similar argument in the integral test, that the series 1 over n with power of p, this will be converges if p is greater 1 and diverges if the p is between 0 until 1. Okay. We know that when p is equal 1, this will be a harmonic. So we could say that this will be, let me write here. Okay, this one. Okay. And this P series, since it is going to be a very easy to see from a series perspective, this series we are going to see a lot. Since later we can see that we could also use some comparison. So we could use this series, the P series, to make a comparison with other series. Okay? To make a comparison. And that should be some pre-introductory to the next topic, which is the comparison, but we are not there yet. So basically, taking the integral test means that you need to be able to utilize the improper integral from the calculus 1. If you don't remember that, we have at least two kinds of improper. Improper in the endpoint and improper within, if that is, so infinite endpoints, or we could say that some axis or some variable that make the value infinite. So we could also see from those 2 points. Like for example, if you remember, we have this kind of graph, right? We have this kind of graph where it's x0, right? This also can be also considered improper if we want to take the integrations. And basically how to solve the improper integral is, basically you are going to integrate as usual. The difference is you are going to input the limit either to the infinite point or to the number that is going to make the function infinity. Okay? Just like this. Okay? This is the improper integration. Taking the limit, like this one. Or maybe the obvious one is the one that we did from the tangent inverse. This is the complete works for the improper integration. This is improper integrations for the infinite points. And the end points was the infinity. Okay, since what we have done, the integration test is not exactly getting the value, right? So we need to have some methods, some numerical methods to approximate how much converged this is, how much is the value. So we are going to see that in the estimations, as the estimation. So you are going to use, I think, a lot of calculation, and perhaps you can use the calculator. So perhaps this is going to be the graph. Okay, so you have a function that is, you see that we have underestimate conditions, which we are going to see that we have some gaps here, and we define in the data science, this is what we call the error, or in our mathematics we call this the R, or the remainder. Okay. So that is, the remainder is when we have some numbers, we divide with another number, and if we do not get the whole number, that there will be something left. That is the remainder. Okay, we could say in the data science, that is the error. Okay. So the error will be defined as the S minus Sn. So the real value minus the estimation. So this will be, so this is the real value. This is the approximation to S. Or let me just write partial sum.
partial sum. Okay. So this is what we call the remainder. So we need the remainder to conclude how good is our approximation. Okay. Now, for the first case, let's start with this underestimate. So right here, this is the underestimate. Underestimate condition, which, if we can conclude from the graph, that the whole sum from this rectangle will always be less than the improper integral itself. Okay. So that's the first case. Now the second case if we have the overestimate. So when we have the overestimate, so this is the overestimate, the whole summations will be greater than the integrations, okay, the integration. But we need to take a different endpoints. If we are using the same functions and we slightly shift a little bit to make it overestimate. So we are going. So I think this is also similar to in your calculus one we did the Riemann, right? Riemann summations. We can take Riemann summation from the left endpoint or right endpoint. It is similar. So we shift a little bit and make it from n plus 1. So we change a little bit here, the endpoints from n plus 1. And we get the remainder will be greater or equal with the integrations. So from what we have here, we could see that our remainder is in between. It's in between these two improper integrations. So we could have from n plus 1 to infinity, this will be less equal than the remainder, and remainder itself is less equal than the underestimate. And of course, all the conditions should be sufficient. The function should be decreasing, positive, continuous. And R is going to be defined as S minus Sn. So basically, this is how we are going to approximate. And how many n, it depends on what we are going to achieve. Because we are not going to compute everything all at once, because it's going to be infinity, right? So we could compare with something that is comparable for our numerical method. Let's say we are going to have like for n equal 20 or n equal 30, how much error it will get. We could see if we can have some differences, some number differences, then that will be the error. Okay. I will give you just some example after this one. Okay. So I think this is all what it says. So remainder estimate for the integral test. So let's see just an example here. So approximate
this series 1 over n cubed using the first 10 terms. So it has the 10 terms. Estimate the error involved. So basically what we are going to do is we are going to set the integrations for the improper integral for this 1 over n cubed, and we know that this is from the P series, right? The P series, we could start getting the result for the integrations. And later we are going to compare the integrations with the sum. Okay? So you're going to add the sum until n equals 10, compare with the integration, and you will get some, you subtract and you have the differences, and that will be the error. Okay? So first is you get the real value, which is you take the sum for 1 over n cubed, for n equal 1 until n equal 10, you get the number. And then you get also the integrations, okay, which is the improper integral. And the idea is you are going to have these two numbers which has differences in number, right? The difference will be the error, okay, the R, the remainder. I think it's quite clear. It's just a numerical method. So first is perhaps we could see the improper integral. Which we can take the sum. Let's just say we are going to take from n until infinity, just to see the form. N is a real value, and we could say that we could take the limit to make it improper. And we know from the integration this will be x minus 3, so it will be x minus 2. So we get limit minus 1 over 2t squared, and then minus minus, we'll get plus 1 over 2n squared. And since if we take 1 over infinity, it will be 0 in limit, so we are going to have 1 over 2n squared. Okay, this is our we can say this is our estimations for the improper integral, and we could compare this result with approximating the sum. So we could take the sum, and basically what we are doing is we are going to take the partial sum for n equal 10, which is just summation for all the possible number. And literally you can do this in your calculator, and this will be approximately around 1.1975 around. And from the remainder estimate, our remainder should be less equal or let me just write fx as the function, so 1 over x cubed dx. Okay, and this will be around 1 over 2 we have here, this is going to be here, 2 10 squared, or this will be 1 over 200. So this will be the size of error. This will be the size of error. So what we are actually doing is, this is 1 over 200 will be the maximum size that can be achieved when we take the n equal 10 through this method. Okay. If we increase maybe the n, maybe 100 or perhaps 1000, maybe it will be different size of error. Or if you want to make it decimals, this is around this number. And also the question can be asked a little bit variation is asking the accuracy within 0.0005. So now we have this, then we want to make it this. So we are going to find how much n if we increase the error, or if we decrease the error here, 0.0005. If we decrease and make it more accurate, so we are going to find the n.
So this is for the number A. For number B, we want Rn less equal. Let me just write the result to 1 over 2n squared. So we want the 1 over 2n squared less equal 0.0005. So if we want to solve this, we can take the n squared and then algebraically solve. We can take out 5, right? So we get at least the n squared. It should be around this. N squared is greater than 1000, or n should be greater than square root of 1000. Or if we want to make it approximately a number, we can say this is 31.6, and we can make it a whole number. That we need to make sure that at least we need n equal 32 to confirm accuracy is within 0.0005.
Ini tadi buat apa ya?
Nah, itu cuman that is just for reference. Okay, this one is just for reference. Okay.
Now we have another equations which relate to this remainder, which we are going to use this one our reference here. We are going to use in the next one. So we have if
we add, okay, so let me write here. So here okay, so since the Rn is S minus Sn, okay, if we add both sides, if we add this is plus Sn plus Sn plus Sn, then we can also get
the new equation here, which we can get from this part over there. So if we plus Sn, then the left part will be Sn plus this, and that one will be Sn plus that, and this will be the S. So we are going to use this Sn using this and adding the error. Okay, we are going to have the actual amount. Okay. So this is the error, and then you can say plus minus with this plus minus with the error. That will be your estimation of the value, the end value. Okay. So this could be done. So for this example, so we are going to have S10 plus, this will be S11 or N11 here. So this will be 10 plus 1, so 11. Let me just write the equation, 1 over x cubed dx less equal S less equal the S10 plus the 10 infinity 1 over x cubed dx. And we get the S10 is 1.19 from here. So this will be 1, or maybe we can write here just to make it reference. Then we have the n. This will be 1 over 2n squared, right? So we are going to have S10 plus 1 over 2 11 squared less equal S plus S10 plus less equal 1 over 2 10 squared. So if we add the error to the S10, we get this will be 1.201664 less equal S less equal 1.202532. So we have this interval. Okay. Well, if you get this, there are many ways that you can interpret this interval. If you want to make it like averagely in one number, you can take this as a midpoint. Take in the midpoint, find the midpoint from here. Just add and divide by 2. Then it's very simple. You get like one single value, which is probably going to be your average value for n equal 10. Okay. So I think this way, I hope you can get maybe a good sense of how the error will place, okay, or how the error would be in your data. Okay, so if you are perhaps later you are dealing with statistics in any forms, it can be perhaps related to some mathematics or some models. You can also think like how many iterations you'll take. Like you can think the n as the iteration, like how many times you are going to get the correct result, like the with accurate pinpoint. Okay. You can also think on the error. Okay. And then and is this a good error? Maybe yes, maybe not. It depends. In some applications, maybe that you need to make sure. For example, if you are dealing with a structure like a big structure, maybe this number is not really that big, and you can simply maybe we could ignore it. And sometimes if you deal with a structure, like you have mechanical property, right, for this building, like if the mechanical property, it has some, let's say, in the property it can have some yield strength, some stiffness, right? And if you know maybe how many weights that it can hold, and you can multiply with, usually if you build a structure you have a safety factor and so on and so forth. And sometimes you need to do some simulations and try to make sure that the data you have is correct, and whenever you pull into the design is correct. So sometimes statistics will be play for most cases in your study. Okay. Okay, that's the size of error. Okay.
Okay, I think that's it for today. Actually, I want to move to the comparison test, but I think we don't have time. Maybe next week. So I think that's all up until here. Let me make small for a while. Sorry, I will take the. Okay, you want to take, if you want to take photo, you can take the photo. Okay, I will. Okay. Wait. Okay. Let's check in for the attendance.